Hello and welcome to session 289 in the AISafety.com reading group. Tonight we will be discussing solve the alignment problem by coupling alignment to capabilities, in other words, gaining capabilities through learning the plan effect mapping by Carl Dybdahl, who is joining us today and will participate in the recording in the discussion afterwards, which will be recorded. Carl Dybdahl is probably most famous for his work on psychometrics, but he is also a software developer at Microsoft, a alignment researcher, and he is well, the most important thing to me personally is that he is in fact a good real-life friend, and that may not be the most important to you, but that is in fact important to me. So thank you, Carl, for joining us today. This is the article in question is an unpublished draft, and that means, of course, that if this is published later at Less Wrong, it may look substantially different. And there is a lot of things that are unpolished, in particular a lot of the formalisms, and it's kind of structured like first there are some less formal arguments, and then it kind of starts over and repeats them with somewhat more technical. So I've rearranged this for this presentation, and of course there's going to be a lot of errors, and there are some things that I don't know and don't understand, and for that I'm very pleased that we'll be able to go through that in the discussion afterwards. Let's start out with the strategic landscape around the research in AI safety. Of course, modeling this is a huge topic, and Carl presents a 5-part model. All models are wrong, but this is a useful model in the sense that if we look at alignment as the task of making an AI do what we really want, that is something that is failing if we are trying to do that in a scalable way. I think that is very true. I don't think that is very much evidence for the fact that it's necessarily that difficult. It's just that we are really not trying as a civilization to do this. On the other hand, capabilities is an area that has increased dramatically. Enormous resources are being pushed into this. A lot of like IQ hours are being pushed into this, and it would be really nice if we could like ride that wave somehow and exploit the benefits of increased capabilities. I worry a bit here that like a lot of the capabilities work that's being done is really architecture specific, and that means that it's not just capabilities that are increasing, like there are like LLMs and like subfields within LLMs and compute and all these kind of things. So it may be a bit simplified. Interpretability is one area where things are certainly moving forward, and would we be able to interpret the world models of large language models, for instance? Like I'm a bit skeptical, but I recognize that I'm unusually skeptical, and I think when Carl is saying that may be possible, I think the consensus is that he is probably right. And I think that is very true, but I also think that it is to an extreme extent about interpreting and very little about modifying. I know obviously some things are done, like making an LLM forget that Paris is in France and something like that, but the design part is very lacking in that. Then we have governance. Governance is not going very well, and for his proposal, it will need to improve, and he considers this a substantial problem for his proposal. When I looked through the proposal, I thought the governance challenges looked decently fine, but I guess that's something we can discuss later. And finally, we have like agent foundations, and this is the central part of like the motivating question for this research is we are getting some work done in capabilities, interpretability, and governance. Can this work help foundations in some way? And the specific area on foundations that we're working in are a part of corrigibility called boundedness. I think many other models of the research landscapes put corrigibility within alignment. So let's talk about bounded optimization. Bounded optimization is like in a very, very vague form defined as like we're not optimizing the entire universe according to our utility function. We're just trying to do a small localized thing. And this small localized formalizing this is a thing that there ought to be some theory about, and there is very little theory about this. And I personally find that I agree that there is almost no theory, and I think the best is hidden in Eliezer Yudkowsky's plane crash Glowfig, and that's of course like really, really hidden, and like I understand that, and I think that is fair enough. But I also think that it is literally there, and the terminology is actually quite good. And I think it's a shame that this this is obviously Eliezer's fault and not Carl's fault. That the terminology is not being used more widely. But I think it would be really nice to use it. And I think there is a sense that we are like reinventing the wheel somewhat. And that's not necessarily a bad idea. Like that's a common rationalist technique to like just try to not look at the actual research on fluid dynamics and try to reinvent it from scratch. And I think you may come up with something new, and the specific formulation here is new, and I think that's just wonderful. Okay, so back to the theory. If we don't have a good theory, then our attempts at making something that is bounded is likely to fail, in the sense that we'll make something that is like too tight and then won't be efficient enough. And that may be one problem. And the other problem is that when we try without a good theory to bound an agent in some way, we may also like leave gaps, and that so we may in fact be both too constraining and too permissive at the same time. And that's really strange in the sense that like bounded tasks, when you just talk about them, it seems like a really natural thing. When you talk about like humans go get the milk, and that's a bounded thing, right? Maybe. Or maybe like the movie Gladiator, like what we do in life echoes in eternity. It may be that the task that we are doing is in some sense not really that bounded. The example that Carl gives is, assume you're trying to affect political change. Would you then decide the best way to do that is to start a company that produces widgets that have absolutely nothing to do with that? That seems like a really strange thing and not really what we want AIs to do. But people do that in fact, right? Right now I'm earning to give, trying to help airports coordinate which aircrafts are allowed to land, and that seems like the something that is really orthogonal to X-Risk. And the example, Karl Marx and Engels were like good friends, and Engels were like funding Karl Marx's work on writing Das Kapital by doing something that was like literally like creating a company that made widgets that had absolutely nothing to do with communism. Okay, so why do we need unbounded bounded optimization? Well, if you don't have that, remember we want AIs to do things that we can't. So we need to have some theory for really, really powerful agents. And I really like that Carl has this point, because a lot of other similar points miss this. So let's give an example. You have a plot of land and you want to build a fusion power plant on this plot, and you don't know how to build a fusion power plant. And you have a really strong AI and you tell it to do that. So that's an example. I'm not entirely sure this is a really good example because it's a really strange situation. Because the boundary in this case, you imagine like you have this plot of land and the AI is allowed to do everything within this plot and not allowed to do things outside except to deliver power and like radiation and things like that. And this kind of spatial boundary isn't really what's going to be relevant. Like obviously the big effect of the AI building this fusion power plant will not be the specific power plant, but the fact that now the technology for fusion power plants have been researched, and that is going to have like a very, very, very large effect on many, many things. So in this way, if we are trying to do bounded optimization, then we need to have a theory that's strong. If we want that to be like the solution for the alignment problem, it needs to be something we can basically, for all the things we want to do AI for, we want to have them do it for in this bounded way. And that is in fact a much, much more difficult question than just have the AI solve the alignment problem in a bounded way. So that's just solving one problem, perhaps a hard one, but only one problem. And that's a lot easier than solving all problems. So that's why I think that would be a better motivating example. Right, let's return to the fusion power plant. You specify what you want, you want power production and things like that. And if you try to do that with a like power production maximizer, then that would like do this kind of standard reinforcement learning and yada yada yada. And this everybody here have probably heard the story that you maximize how much power you produce, and then it takes over the world, and everybody dies. So we want to get around this, and the formalization that gets around this hopefully starts with effects. And the key technical challenge here is that we are not maximizing a utility function. We're not building an AI that maximizes the power production. We want an AI that looks at the effects and in the world. It's a bit unclear to me whether that, like, obviously the superintelligence is in both cases just tracking everything, because like it's a superintelligence, of course it's doing that. But it seems kind of like homomorphic to an indicator utility function on these effects. But we will return to this, I expect. So what's an effect? Well, it could be something like remove something and create other things, power, things like that. And these effects are specified in the AI's self-learned world model. And that topic, self-learned world model, I promise you we'll get back to that. That is pin number 1. But I also, like, this isn't really specified that clearly. Like, what is this binary just remove or not remove? Like, what is the concept space here? Like, I think I would understand this better if I had some example of things that are not effects. And maybe nothing is an effect and everything is an effect, perhaps. And these effects are intimately related to plans, because plans is what cause effect to some extent. And precisely the formalization here is somewhat up for grabs. It's possible it can be done in other ways, but the key thing we want the AI to do is to learn the plan effect mapping. And obviously this is intimately related to causality, like how effects cause other effects. And like the precise difference, like between, like, causality is more than just the plan effect mapping, but like separating out this concept is probably something that would make me less confused about this. Okay, learning the plan effect mapping means to have like a joint distribution between like plans and effects, and we'll see how that can be used in a rather beautiful way later. One problem with this, of course, is that the AI is part of the world. The AI is embedded in the world. And that does, in fact, create a number of problems. Like, there is, I think Abram Demski has this sequence on embedded agency, and it shows a lot of problems. Like, and it would be really nice if we could avoid that, but obviously we can't avoid that. Like, we need, because we want the AI to actually do things and learn things and like be a part of the world. It would be nice if we could avoid it. We can't avoid it, so we need to deal with all this messy embedded agency stuff. But let's try to take a reasonably simple example and see how far we can get with that. And that would be programming. In this case, we have the source code as an example of a plan. And then the actual execution of the code is then the effect. And the effect obviously depends a lot on the context, like what is the input outputs and state of the system and all these kind of things. But this is an example of a clean separation. And when we try to look at this, we have a really tight feedback loop, because you can literally run it at the speed of compute. And that means that this is a really powerful tool for learning the mapping between plan and effects. So I agree, and I think this is in fact perfect for capability research, and I would be surprised if OpenAI is not doing something like that right now. The hope is that the AI might be able to learn this in build some kind of model using a higher abstraction language, and of course, because like Turing machines are extremely complex, then having some kind of language that is efficient for working with these kind of structures. Like when I think about Turing machines, my head starts to hurt very, very quickly, unfortunately. And like having a strong language for that seems really, really valuable. And I agree, it would be wonderful. And I unfortunately expect this to be mostly unintelligible to humans. And that's a thing that we need to grapple with, and maybe just not for humans to do this. Carl has tried to make some toy examples and not really finding anything that's really good. And like my intuition, this is my weak intuition for the future, please don't update too much on this, is that this is actually something that will succeed. And GPT-8 or something like that will be able to use this to build this brain in a box that people thought we would be able. Like if you go back to this is a total aside, right? If you go back to 2002, Eliezer Yudkowsky was sitting in MIRI, in the Singularity Institute, and thinking that they may be able to build this, and it turned out that humans are just not smart enough to do that. You can't do that with 150 IQ, but I think you may in fact be able to do that if you have an IQ that's like 220 or something like that. And so I think the way we'll do it is not by understanding intelligence, but by building an LLM that can then do this. But unfortunately also, I don't expect there'll be any humans left by the time we get to GPT-8, so it's kind of like as somewhat of not really a consolation. Okay, so let's see how can we actually do this bounded optimization. The core of the proposal is the bounded feedback loop, which starts out with the operator describing the total effect that he wants. And this is the topic of whitelisting the effects. And I'm gonna have to put another pin in that because that's another rather large topic. We'll get back to this, I promise. One important thing here is that the effect must be precisely specified. So it can't do more things and it can't do less things. And one thing in particular that's really important is that we can't have the operator specified in this effect. So the effect cannot be do what I want, because then you're giving that as an input, and that's something that the AI is obviously going to be adversarially optimizing for. If you trying to fool you into thinking that it actually did it and then it didn't do it or something like that. So that's an important part of the effects. And I agree, but there is obviously going to be an effect, even if it's not what it's optimizing for. It's going to have the effect that the operator is like satisfied or not satisfied with the way. That seems like an impossible way, and I think precisely how that is avoided is something I think we'll get back to some extent. So here's a cute thing. Like we had the joint distribution between plans and effects. So how do we plan? Well, we conditioning on the effect that we want. Like what are the plans that can give that, and we can evaluate our plans by conditioning on the plan. Then we can see like what effects would that cause. So this is kind of like the planning and evaluating feedback loop that ties into this bounded feedback loop. So it starts here in a very idealized form with the AI taking some actions that are later evaluated. Of course, we hope that the AI is not that smart that it can just literally take over before the first evaluation step. And probably if we make it very small, it seems like a reasonable assumption. Then the AI needs to observe the results of its action. Carl is much more pessimistic about this than I would have thought. I am thinking like, yeah, sure, just sensors. And once the AI has observed the result, it updates its world model. Carl writes, you should try to learn as much as possible, and the hairs on my hands start to stand up when people write as much as possible, because that sounds very, very unbounded. And this has the obvious problem that if it updates the world model, the world model was where we had specified the total effects, and so it updates them, and then the total effects may not make sense anymore, right? We may break the ontology. So that is in fact a real problem. How do we do online learning? And then we evaluate in the way just described, and then we look at, the AI looks at, is there a plan that can lead to actually obtaining the goal? If it's not, then we'll go on the next slide, we'll talk about that. And if it is, then the AI will report potential problems and deviation and things like that, so it can be stopped. And of course, this requires solving the stop problem that hasn't been solved as far as I know yet. Carl, you have raised your hand.
There's also a couple of things, right? So because we're not just taking actions immediately, right? We are saying, okay, we get this plan, right, which specifies some actions, but then before taking the actions, right, we can say, oh, what effect do we expect from this plan, right? So if this doesn't match with the specification, then we know, oh, there's something, uh, you know, that needs to be handled. Yeah,
Yes.
more on that later.
Yeah, and I think I actually have that on the next slide here, because like this entire feedback loop, the way I'm thinking about this is that this is something that the AI simulates within its own head, in the sense that if it's trying to build a fusion power plant, it doesn't just start to build the fusion power plant and then it goes through this loop, and then after it's like halfway done, it figures out, oh, I can't build a fusion power plant. So obviously it figures this out already in the planning phase. So that's like my thought about how this would actually work. So let's assume, and thank you for your comment, by the way. Assuming that it figures out that it can't actually do this, what should it do? Well, it should try to find bottlenecks using backchaining, or I guess there are multiple ways, but the definition of bottlenecks is somewhat different from what I would have thought, because a bottleneck here is a relaxed problem. And for a fusion power plant, that would be something like lower temperature or something like that. And this is like finding relaxed problems and trying to solve them is one thing, but there are other kinds of, when I think about a bottleneck, I think about things like there's not enough funds, there is not enough space on the plot to build this, I'm not smart enough to build a fusion power plant. That is kind of the thing, like the reason I can't build a fusion power plant is because I don't have enough funds, I don't have enough space, I don't have enough intelligence. It's not because that I'm like, I can only build a reactor that gets like 1000 degrees hot. That's not really how humans think about this. And so what bottleneck should you take? Carl suggests the simplest bottleneck. Like simplest is obviously one criteria. I think like most restraining, or like most promising in some sense. That's of course much more vague to say most promising. And then the AI can request resources to experiment with breaking through it, or it could potentially also just request enough resources that it expects it can break through it. But this is like a quite different way from how humans solve most problems. And I think this is a problem for this algorithm that if it's very different from how humans solve problems, there is a substantial risk that it just won't be performing very well. And there is also the problem that requesting the resources, if we assume that the problem is one where we can like gradually build up to a solution, like you have a fusion reactor where you can gradually slowly increase the heat and then eventually you'll break even and eventually you'll make a lot of energy, then that would work. But there are a lot of things that doesn't really work like that, and like it may be that fusion is just much harder than we think because of some strange thing that means that basically you need to build the entire sun an entire star in order to really do fusion. This seems like the kind of problem where this approach would not really be successful. Another, let's return to this that I talked previously about, with the input-based and output-based. With the when we're considering the effects, we are not optimizing for the inputs, because like trying to fool the human into believing that we're building this reactor, because we're not exploiting the input at all, meaning that we are like not building an AI that is optimizing for us to be happy about the fusion. We are making one that only cares about the specified effects and not what we actually want. And if there is a difference between these two things, if our specification is not good, this is what humans would generally call a bug and not a feature, if there is this kind of misspecification. I think that may in fact be the literal definition of a bug. So this may be an unavoidable problem, because if the specification take you the outcome as an input, then you're vulnerable to adversarial optimization. But if you only look at the outputs, then it'll be more bounded and unpredictable. Like the sentence was a bit unclear, and I'm not sure I'm really stating this correctly. and it gets somewhat worse, I'm afraid, with the in the section stay covariant and avoid contravariance. Like, let's ignore these two words for now and just look at the input based and output based. Like, this is like a very way where in the input based you give a utility function and then say please maximize this, and the output based the AI gives you a probability distribution. In the input based, yeah,
so it's more like you give it a probability distribution. You give the AI. So the thing is, a utility function takes a state of the world as input and gives a utility for it. Now, you could sort of say, oh, a probability distribution also takes a state of the world and gives a probability for that. But, you know, sort of, if you want to look at it mathematically, or like category theory is like very fashionable, right? That's not sort of, you wouldn't formalize the probability distribution as taking an input in that context. Because, for instance, if you have some function that you want to transform the probability distribution with, say squaring, right? Then basically you sample from the probability distribution, square that, and then that's where you get the samples from the new one. And you know, it's kind of convenient to describe a probability distribution with like you know, a density function or whatever. So often people do that, but then to actually talk about the transformations and so on, you have to do some weird integrals and so on. So with a probability distribution, you can think of it as like, oh, it's a function from a random number generator to something, right? And then the something that we're sending it to is an output, right? So it's you specify, oh, I want something that looks like this, right? I want something that looks like a well, not something that looks like, because then we're starting to talk about input, but I want like a fusion power plant. Give me something sampled from this distribution, right? And I should say these are sort of, like I mentioned in the post, these are sort of like somewhat metaphorical, right? But you know, you say, oh, give me something that like there's a difference between pointing out this is what I want versus give me anything. I also reference Alex Turner's something about adversarial. I have a link in the post about, you know, and post that explains why we don't want to do input-based stuff, right? But basically your input space will be exponentially big, right? And then what is the chance that you can make something that, you know, describes what you want in some exponentially big space where it can choose anything completely adversarially? It's way smarter than you, and it gets to choose whatever it wants. That's not very likely.
yeah. Uh, like I guess this is probably something we will return to later, and also the relation to covariance and contravariance. So I put this up here because I thought this was kind of an image that I felt kind of explained this, but I think we will just return to this later in the discussion.
That image is definitely relevant. But yes.
Great. So I promised to talk about whitelisting, so let's talk about it. So let's start with a somewhat simple example, assuming that we have like perfect whitelisting. Santa magically appears with a list of effects, and this is like the perfect list. What would that give us? Well, first, it may unfortunately be impossible for us to read this list, because the AI in its world model may use concepts that it can't explain to us because it's simply too difficult. And I think in particular when you're talking about something like the perfect, like the limit of intelligence, probably the most intelligent, the highest intelligence possible is using concepts that humans can just basically totally never understand. It's my intuition. I don't actually like obviously know about this. If we had that, then one of the key ways we could control the AI is by like literally measuring the effects. And I think measuring becomes a lot harder when we're talking about things like a lot of the effects are things that we can't actually measure. Like there are things that happen in the future, perhaps in the far future. A lot of the effects are things inside people's minds, or things like that. And I think like talking about measuring, even if we know what the effect is, someone can say the effect will be this, then measuring seems really hard. One thing it does provide us, however, is the nearest unblocked strategy, which is a classic problem for a superintelligence. If you put up, say, you can only do like these things and nothing else, then the AI is like trying to find holes in between our rules, and it will probably be able to do that. Perfect whitelisting avoids this because there are no unblocked strategies, and that of course fails once the perfectness is relaxed. But it is also like, obviously, if we are literally omniscient, if we assume that we have a Santa that can give us the truth, then we don't actually need this proposal. I think if we assume that, we can find some simpler proposals that will work. So the problem is, what happens if we don't get perfect whitelisting, but only very good whitelisting? What would that give us? That would still give us a lot. We would have a lot more insight into the AI's behavior. We would get better feedback loops. We would get better iterative designs. The task of alignment would be like a lot easier, and predictability would be another thing. There would be so many good things to come out of really good whitelisting, and it would be a wonderful thing to have. But it is also a lot of work. Even if we have like some really good language to talk about this, a really good model, then specifying. So I'll need to do some editing work here at this point. Okay, so we have very good whitelisting, and that gives us insight into the AI's behavior, better feedback loops, better iterative. And the problem is that specifying all the symbol effects is a ton of work, to say the least. Like imagine you have a normal power plant, how many pages of uh, like design specs there are for a normal power plant, and I expect a fusion power plant to have way more. That's just a huge amount of work, and a lot of it is not really simple. There is a lot of gotchas in this, and I think this is a very dramatic disadvantage compared to if you do something that is like input based, where you just say make a fusion power plant in a way that will make me happy. Like even if you have a really deceptive and horribly misaligned, then it's still a lot easier to do that, right? Um, and one thing that would happen if your whitelisting is imperfect is that you would get too many warnings. And the AI, like if you haven't really whitelisted all the things that you ought to have whitelisted, and you forget, like, okay, the fusion power plant, all these isotopes need to decay, and that's actually going to take a long while. If you forget about this, then the AI will warn you more. And the bigger the difference between your whitelisting and perfect whitelisting is, the more warnings you'll get. And that's of course, to some extent, it's a nice thing. But unfortunately, too many warnings is also something that means that you turn the boundedness down. And then if it warns you way too much, then you turn the boundedness way down too much, and then this feature that it warns you too much causes you to actually lose the safety guarantees, and then we die. So I would consider that a bug, the fact that we die as a side effect. One very concrete kind of side effect would be noise. It's really hard to do things like building a power plant without making noise. But of course, noise is like figurative small effects. Like we're building a power plant, that's a big thing, but probably there's going to be a lot of small effects. Um, and there's been some work on formalizing this under the heading of impact measures. And probably the AI's world model is good enough that it can say to some extent that the noise isn't that important. It's totally acceptable to make some noise while you're building a fusion power plant. Um, and so let's assume that some person suggests, the operator suggests that, okay, we actually just whitelist this and say we don't care about the noise. So what would be the results be? Well, Carl answers this. Then um, there is an effect which is that people nearby will hear me, and that will affect them in super complex ways. And like this is really complex, and it doesn't matter. So we'll just ignore this and just whitelist the noise. The problem is, of course, if we whitelist noise, then we've accidentally also whitelist information bearing noise, which includes talking to people. and that also falls into affecting them in super complex ways, and that means that the whitelisting is then accidentally too wide. If you just do this by just whitelisting people hearing it, and then you might have suddenly whitelisted too much. Carl, you have a comment on that? Maybe I misunderstood.
So I think, the AI will have to model, the AI will be modeling, the world generally, right? So it will be modeling, okay, whatever I do, there's gonna be some noise, right? But most of the time, this noise is just like not gonna have any effect at all, right? Like most random noise you do is not gonna have any effect, right? So you're gonna have some category that's like if you make some sort of like self-supervised world model, you're probably gonna learn some category like there's noise and it doesn't do anything, right? And so if you go and build this, um, do this like power plant or whatever, right? Then it's gonna try to build it, and by default, it's not gonna do anything, right? But you know, if there are some people nearby, right, then it's gonna need to model the effect of the noise on those people, right? And one and then that's where you get different kinds of things, right? Because then it needs to represent this noise that happens near people differently from noise that just happens generically, right? And noise that happens near people, right? That will also affect people in different ways that will be modeled differently by AI. So if you put a whitelist on generic noise and maybe noise that doesn't affect people in any predictable way, right? Then that doesn't mean that you have a whitelist on talking to people about something that it's trying to do, right? Because if it's trying to achieve something by talking to people, then it must have a model of what will this talk do, which means it's represented differently from all the other noise.
I think I agree with you, and I think what you just said, like with how it should affect people, the way you described the limitations of how it should affect people is in fact a totally fine workaround to the specific unblocked issue I mentioned. But I would also say you said literally, I'm quoting here, that affect them in super complex ways, and talking is within this set of super complex ways. So that this super complex ways needs to be strengthened
So
to not in any predictable way or something like that. And if
so
we did that, then the nearest unblock strategy would
so I link in this section of the post, I link a post by John Wentworth where he points out noise simplifies, right? Which is, if you have like a butterfly that flaps its wings, then it's gonna cause hurricanes or whatever, right? But it's not gonna cause hurricanes in any predictable way, right? So if you want to model the climate, then, or like model the weather, I guess, whatever. It's kind of weird because climate is like average weather, or whatever. If you want to model the weather, right, then you are gonna use some ontology that simplifies away the flaps of a butterfly's wings, right? Because they are too complex to be modeled. Um, and of course, then there's the question of like the AI is much smarter than us, so it can model things we can't, and that's of course complicated, right? But
yeah. Thank you for that answer. I think that that certainly cleared it out substantially for me, that this is not just like this example is not just a like a random patch, but the fact that it's not predictable is in fact like a meaningful full patch. Thank you. The next issue is on micromanagement, because if you imagine that you have the AI working on this plot, then like while doing that, it will take some like instrumental actions like paving everything off or something like that. And there are so many things it can do within like while it's building this fusion power plant that uh, that we can't explicitly whitelist them. That would be impossible because we don't know how to build this fusion power plant. So we can't literally whitelist all the tasks that it's doing like within this plot.
Um, and like I think like when I read it first, my thought was like that just means like instrumental actions toward the final goals can't be stopped by this proposal. I think that's an adversarial rephrase. I think in fact that is not what's going on here. But let's talk a bit more about how to solve this problem. So the first is like in some meaningful sense, like we want the fusion power plant is a large thing, and all the things that's happening inside ought to be small, and that in some sense. So it ought to be possible, right? And I haven't read the theory of impact measures very much, but I don't really think that the precision is the big problem. Uh, like it's not that we have a hard time saying this is small compared to this. It's that sometimes the impact measures like just totally dramatically fail. That's my understanding. I haven't read enough about it to like really have a strong opinion about that. The second, yeah, I haven't introduced a Markov blanket yet. Like, let's say, except we could just whitelist everything that happens inside the plot. Um, and that would be another option for how to solve that. Saying, okay, we don't actually care what's happening inside the fusion plant as long as it actually produces power. And this has some obvious bad possibilities, like the AI could like build a robot army on the plot. That would be an example of something we would not want to happen, even if it technically has no effects outside of the macro blanket. Another issue is that another way to solve this is like when the AI asks us for something about this, uh, then like the AI is saying that it has a world model, so it can explain to us it needs to like connect these pipes, or it needs to like uh, bury some radioactive waste or something like that, and it won't have any effects outside of the bounds. So we should probably mostly say yes. And I think it works for relaxed problems, but like most of the thing that the AI is going to ask for is probably going to be extra resources and effects. So uh, like I think the micromanagement probably isn't going to be the key problem. The key problem is that the AI is going to say, actually, what I want is to cause the effect that people know how to build fusion power plants, and that may in fact have some like weapon implications for how to build weapons or something like that. And like that is the core problem, not so much what's going on inside the actual plot. Finally, that was whitelisting, and let's finally get to the self-learned world model, which is a substantial task. So, what would again the perfect world model look like? Well, it needs to be self-learned because we can't put it into the AI. That's just totally impossible. And not only must the AI be able to learn, it needs to be able to learn it like in a competitive sense. Like it needs to be something that like we're hoping that this is something that can overtake what OpenAI is doing. So if it's something that costs like more than 7 trillions, then it's probably not worthwhile. It needs to be comprehensive. It is a substantial problem if it doesn't consider like pollution would be an example. If the fusion problem model doesn't think about pollution, that's a big problem. It needs to be well factored into specific parts, and uh, 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 each of these effects that we are looking at needs to be a separate factor. And these factors can need to have some kind of organization, because if it's just a large bulleted list without any organizational structure, then it's impossible for humans to really understand. It needs to have some kind of mapping in conceptual space that makes sense for humans to understand. And also we want the parts to map to human concepts, so to something that humans can understand, and not only to just human concepts, but interesting concepts. And that is not all human concepts are interesting. It needs to be efficient, like not waste too much when it's. We talked previously about how difficult to learn. Now it's about how difficult the world model is to use. It needs to be efficient, and needs to be so it needs to like not take too long, and also needs to be effective. It needs to actually accomplish the goal that we're trying to do. And finally, it needs to not have any illegible parts, because if there are big parts of it that we can't understand, then that may be where the danger hides, right? We can't write these things in a world model that we can't understand. And the problem here, of course, is that here are 10 requirements, and for each of these requirements, assume that we don't get it. Like, assume that, like, obviously, if we assume it's not self-learned, then it's impossible. Assume it's not comprehensive, then that could also fail. And in general, I think if we remove one of these desiderata, in general, what we will get is an AI that is able to kill us. And that is, in fact, a rather substantial problem. And I think the problem also is that these requirements are kind of hard. Like, this is a tall order that we are putting up here. So there is a discussion about wirehedging, and I'm not entirely sure I understand entirely both the discussion and the relevance. So I'm going to go over it very quickly, and perhaps we can return to it in the discussion. So we have ICSI, the reinforcement learning agent by Marcus Hutter proposed, looking at all hypotheses at the same time, weighing by the length of the Turing the program that makes them. It's a non-embedded program, and it doesn't have a pointer to whether the human approves. And there's a description about why, and I'm somewhat confused about that. Like, I think actually it's something that it ought to be like very easy for it to like have sensors that could do that. But IC needs to have a reward counter. Like, that needs to be a direct sensor, and since it can understand this, it is motivated to wire. And if we look at something like AlphaGo, that's an example of an AI that has a good world model. Like, the IC has like literally the worst possible world model, right? This is just totally incomprehensible. Like, if you look at the space of all possible Turing machines, you will go crazy in short order. But AlphaGo has a really nice world order. Like, there are these 19 by 19 squares, and AlphaGo does not wirehead, right? That's really obvious. And even if we gave AlphaGo the option to wirehead, it will not wirehead. So if we assume that we give it the option, so we add, instead of the 361 intersections that you put the counters on, you add a second, which just auto wins, which like is the reward signal. Have we won or something like that? Will the AI want to take over this? Well, is there a way to avoid doing this? Yeah, sure. It's really easy. We've built the world model into AlphaGo, so we can just do that. Um, Carl is arguing that it's because we can express concepts like, will we win if we do these kind of actions? I think the way DeepMind would go about this is that they have just a literal pointer to the effect that the model has put a counter on this reward, has tried to take over the reward button, and then just define a reward function about winning without using it. That's how I would go about it, because you understand this world model, then it's really easy. Carl's specific argument about how to avoid it, I couldn't quite make it work. How do you, if you know that you will win if you take this action, how does that help you avoid wirehedging? Like, it may not be that interesting, in fact, because like the precise way to do this. And like, there's a bit more about wirehedging, and I think this is not that central. So perhaps we will return to this in the discussion. So let's talk a bit about the structure of the world model. Because if we have a world model, then human values, of course, is a famously slippery concept. That's why I think we should go for corrigibility and not alignment. But finding a concept like a fusion power plant is probably a lot easier. And we go back to this type theory, where the optimization algorithm needs a model, a world model, and the signature of the model depends on the optimization algorithm. So a wirehedging prone world model will be one where the AI predicts observation from past observations and actions, and I guess also predicts rewards. That seems like a requirement. Where the non-wirehedging model predicts observations and also latent values from observations. And the bounded optimizer, that's the type signature is still outstanding. And I should say here that Miri tried to look into this kind of thing and failed. So I think there is unfortunately reasons to be a bit pessimistic about whether it will be possible to find a good type signature. But I'm also I shouldn't most confused about this. What I'm less confused about is comprehensive world models, in the sense that I'm in fact even more confused about that. But I'm more certain about my confusion, in the sense that like we really need a comprehensive world model, because once you start excluding things, then you get into substantial problems. And it may still be possible to have a sub AI or something else that only has a particular domain, and maybe you can, if you in particular, if you're just trying to solve a single problem, like the alignment problem, or doing one pivotal action instead of being able to do literally everything. In that case, you may be able to do something like, I think it's sometimes called like the lonely engineer, or like domaining is I think a term that Eliezer Yudkowsky is using. It may be possible to do something like that, but really, if we want to do everything, we need a comprehensive world model, and in fact, many tasks need a really broad world model. Like that's kind of part of, like we talk about general intelligence, but one thing that I think Carl and I agree on is that comprehensive world models are difficult, both on a conceptual level and on a computational level. And particularly if you need really high quality super intelligent, then this is something that you're not gonna get for free. Well, perhaps because like OpenAI is maybe doing our work, because they are putting trillions into building literally a really large world model, and maybe they will just figure it out. And unfortunately, it seems like they have already done that. They have built a really good world model, but unfortunately, it's in a giant inscrutable matrix, and that isn't really very nice for us, because like this isn't something that will allow us to talk about new effects, just because like obviously GPT-4 can like do novel things, can make new kinds of drawings, but it can't really explain them to us, because uh, like it's just a giant inscrutable matrix. It's not like DALL-E can say, oh, I'm putting this drawing here for this kind of reason. And of course, this is like the central problem, because like capability researchers have in fact built this, and they've built it using a giant inscrutable matrix, and that means that they're not going to solve the same problem one more time. So they won't in fact solve this problem for us, because they have already solved it, just not in the way we want them to. Another big property we want from this world model that I alluded to previously is factoring, because we really want the plans and the world model to factor into conceptually distinct parts that have a low coupling between them, like into effects would be nice. It would be nice to have like high coherently modules with low coupling between them. That would be really nice. If we can get that, we will have a much greater understanding. It would also be much better for the AI if it had a world model that was like that. It's really hard to do in general. Like anyone who's tried to refactor an ugly code base knows that that is actually really hard. But um, I think that implies a substantial alignment text. If you are comparing like the world model that OpenAI has built in a giant matrix right now, with trying to make a well-factored model, then like turning it into a well-factored model is going to be an enormous task. Um, but and this also requires a world model that is compositional, that we can add these different components together. But if you get that right, then if you want a compositional world models, then you need to explicitly model the effects, and that of course makes unintended effects less likely, and you can like point out bad effects and things like that. So it would in fact be really good to have one of those. Um, and one thing that I worry about is that two of the key objects that we're going to have to grapple with are neural networks. And there are two kinds of neural networks. There are artificial neural networks, and there are biological neural networks, both of which are probably going to be really important. And I don't think they factor cleanly, or can be made to factor cleanly. Carl, please go ahead.
Yes. So it's not that I think that every part of the world model needs to be factored nicely. Oh, sorry. It's not that every part of the world model needs to be factored nicely, right? Because I think it's basically fine if the world model has some complicated neural network on some boundaries for like doing some computation or something that we don't know. The part that I especially think needs to be factored is sort of the representation over space or something. Like the simplest might be you could imagine modeling the world in a bunch of independent chunks, like a cellular automaton, right? Then it's factored nicely. And even if you don't understand exactly how it's modeling a chunk, right? Because it's like locally connected, you can say, okay, what's in this chunk? And like you have some nice representation for that. So you can say, oh, I want, if you have a strawberry, then you can say, I want another strawberry. Or, if you can say, oh, what's in the chunk boundary? And then you gain basically a lot of interpretability, and like a lot of the proposals sort of depend on this, right? But sort of the neural network being factored is not so much the important part. And I sort of discuss, I think, in the post why a chunking the entire world isn't feasible. Basically, it's computationally intractable. You can't really model the world as cellular automaton because then you have to model the entire world, and that's too expensive.
Okay, great. I think we will return to this. Um, but I will keep my answer for later. So let's talk about how could we think about boundedness, and how could we actually try to formalize this. So we assume that we have this world model factored into spatially localized variables. So this is an example. It's not a really good example. This is kind of like a causal Bayesian network where you have like some inputs that are both like the context, like we're building a fusion power plant, and we have like this is the plot, and these are the regulations, and we also have some actions that go into this, and then at the bottom we have some kind of effects. Hopefully, some of this will be that we get power out of it, and a lot of internal things are happening inside. Um, this is like a causal Bayesian network or an influence diagram, and we assume that this is a world model that satisfies all the world model serializer that we looked at previously. In this case, we pick what is called a Markov blanket. So we look at our entire huge world model, and then we just look at one area that covers all the useful information. We may want to have it like it's not that important that it's like the minimal, like the Markov boundary that is minimal is okay, that it's bigger if that makes it easier for you to understand. So we pick some a much smaller set, and say we will only look at this. The next we'll need to do is to perform a counterfactual surgery, like Judea Pearl suggests in his book that I don't own, unfortunately, and that is kind of a problem, and I really ought to buy that. Because like I tried to Google for Judea Pearl and counterfactual surgery, and the only thing I really found was Eliezer Yudkowsky, who has done some work on timeless decision theory that was using this, and I could in fact not find a definition of counterfactual surgery. Thankfully, Carl has provided like kind of a very brief description of how this is done. But so we look at the variables inside the Markov blanket and then just like cut them out. That's like the surgery part, and replace them with a program that is representing your desired effect. Um, it kind of seemed to me that this is just like maximizing within this area, but that I think that may not be what it is. Um, so this is possibly an area where I'm gonna meet Carl and go to the library and borrow a book, I guess. But also like whether this is actually correct is like doubtful. Like Markov blankets change dynamically, and I guess we'll return to that as well. We have coherence theorems that says that like if you try to make like a less rational agent, it would want to turn itself into a more rational agent, a more coherent agent, and if you try to make a bounded optimizer, will it want to actually become an unbounded maximizer? Well, maybe. Um, we certainly have something that, like, bounded optimizer will do things that are not strictly rational. So maybe some of the coherence theorems that we have won't apply. Um, Maybe the AI will like leave money on the floor, and it is possible the AI will leave money on the floor. And I predict, because I know humans, that if they build an AI that leaves money on the floor, they will adjust the AI until it no longer leaves money on the floor, because people would actually really like there not to be money on the floor. Um, the second reason is that, like, probably this bounded optimization will be utility maximizing on the margin. And I think this is a separate problem, but potentially a really big problem, that um, uh, in concept space, the like implementing this may very well be something that is like a unbounded utility maximizer plus something that is like a very small extra part that perhaps will end up being kind of grafted on top of that. And if it's grafted on top of that, then it could very easily be removed, perhaps by itself, perhaps by someone else. And I think this is a problem. The third reason is that, like, okay, the space of optimizers is very large, and bounded optimizers is just a tiny fraction of those. So if you have a theorem that says most agents will want to be more coherent, then that may not apply for a very small fraction of that set, and that's of course true. But we kind of need a proper argument for that, and perhaps Carl has one here.
So, I mean, the main thing is like in the context of like the AI leaving money on the floor, right? Where it's true that, you know, if humans could get more money by telling the AI to, you know, pick up any money it sees, right? Like, then people might want to do that, right? But, you know, part of the alignment problem, right, is that, you know, we don't really know how to do that without also telling it, hey, take money out of people's pockets and take money from tables and, you know, take money from everywhere, right? So the idea is, you know, if we tell it, you know, like if we make an AI that only tries to achieve a certain total effect that does not include taking money off the floor, right? Then, you know, the AI will not be taking money off the floor. It will not be taking money out of people's pockets and so on. And there will of course be people who think, but is there a way that I could get it to collect it, you know, money that's just lying around in places, right? But, you know, if they do it by removing the bounded optimization, then, you know, you get all the problems with unbounded optimization. And so, you know, that's not necessarily a thing, right?
Yeah, I agree. This is a
Yeah.
I'm making an isolated demand for rigor, in the
Yeah.
sense that you're making a proposal for how to build a safe, and then I say, yeah, but people would just remove the safety guardrails. But that's like a problem that
Yeah.
any alignment proposal is going to have. That, yeah, you make the guardrails, and then people might take them off. So
So I guess to answer your question about, you know, the small fraction thing, right? Um, I'm sort of thinking about it in the context of, for instance, Alex Turner's argument for power seeking, right? I don't even think he likes that argument, but I don't agree with him about why he shouldn't like it. So yeah, I'm gonna keep using it even if he doesn't like it. So his argument is that an AI will be power seeking because if you look at like the group of all the ways you can permute the utility function, right, such that you assign utilities to different outcomes, basically, right? Then most elements in this group will bring your non-power seeking utility function to a power seeking one, right? And therefore the AI will be power seeking. But the problem is if most elements of the group also bring us away from the bounded optimization, like if most of them give us a utility function that's not really a result of this bound. Like we have some coherence theorems that say something like any good agent is a utility maximizer. So it says, you know, there is some utility function for all of our bounded optimizations, right? But, you know, if those are just a very small fraction, then it's possibly very compatible with, say, Alex Turner's theorems, right? And he has some theorems that say, oh, it's going to be exponentially many in certain cases and so on. So I think one could look through those and sort of see if they work out in some specific way. But I don't necessarily think that we need a stronger argument unless someone can take his theorem and produce an argument in this case. But that's to be decided, I guess.
Okay. Then there's a part of it's the section is labeled Mesa optimizers, but I don't actually think it talks about Mesa optimizers. As far as I can say, it's only talking about sub agents, which is like a related problem, but a and here the question is, to what extent are bounded optimizers reflectively stable? Does a bounded optimizer want to continue to be a bounded optimizer, or will it try to make a sub agent that is not a bounded optimizer? And the way I think about it, and that may be a different way, is it kind of depends on how the bounded optimization is implemented. You can imagine it being implemented in the goal or in the planning. So in the very extreme case where we just we take a utility maximizer and then we don't change the goal, but we just force it to only make plans and take actions that fit under the Markov blanket, and we graft that onto it in some way. In that way, if it's capable of building a sub agent that can act in an unbounded way, then it will want to do that. And so it's not reflectively stable. It will want to avoid that if it's implemented not in the goal, but in some kind of restriction. Now we are returning a bit to the topic of corrigibility, where Carl introduces unassertiveness as a like don't leaving your fingerprints on the future, but to maximize others' preferences and not your own. And I think like you can obviously formalize this, like just like point to some other person, maximize that person's preferences, and you end up with that person being like on a heroin drip or something like that. That seems like an obvious bad way to do that. And I'm wondering if Carl has a better one in mind. And of course, the problem also is like whose preferences, like should it be like rich people or whatever? That's a governance issue. The hope is this unassertiveness will be kind of like a vending machine. I kind of feel like a reference to like tool AI. But if we compare unassertiveness with boundedness, then we have two by two options, right? You can have assertive and unassertive, and bounded and unbounded. It becomes I always get them confused because like with assertiveness, the is good and like unboundedness is bad, right? So but if we assume that you have an unbounded and assertive agent, like that's like literally the worst of all possible worlds. That's the non-corrigible, the thing that wants to like push its values onto the entire world and will be like a utility maximizer that might handle world security, yeah, and it will handle world by security by killing everybody. That seems really obviously unsafe, and fair enough, right? And you could also have like something that acts unbounded, but on behalf of some other subject, and that's probably would affect the subject. That's the classic alignment problem that you've just built something. And you build an AI and tell it to maximize my preference. Well, then you need to solve basically the old style alignment problem. Um, and uh, and then of course the thing that we are really interested in is the bounded unassertive. That's the most corrigible, and that's kind of the thing that we're hoping to do this. Um, Carl writes that he's inspired by ideologies doing unbounded, unassertive, and like this is here I am obliged by law and by custom to give the standard warning that if you look into these kind of ideologies and politics, you will be mind killed. Obviously, Carl knows that, but I have to give that warning. So, Carl, tell me, you have some comments on this.
Yes. So I mean, I would sort of like say that maybe you've misunderstood that, or maybe I've had a typo or something. So um, I'm specifically inspired by critiques of ideologies that are doing unbounded unassertiveness. So the problem, or like part of the problem, is if the operators of the AI are too unassertive, right? If you say, oh, I don't know what I want. I don't know if I want a fusion power plant. I don't know if I want a what's it called? Those things where you put the star into. Uh, um,
Dyson sphere.
but yeah, Dyson sphere. You know, if you say, oh, I don't know if I want to kill all animals or if I want to like have nature protected or something, right? Well, because then you are going to go into this issue of, oh, we are going to have an AI that figures out human values for us and then forces it on the entire world and so on, right? Um, and and like that's sort of I guess the intuitive way for utilitarians to handle things, and I think we'll get back to that later when we go back to the discussion and to Karl Engels and Marx, Engels, and like effective altruism and so on, because I think that's like a very interesting and actually important for understanding this proposal part, even though it's the mind killer, but yeah.
Fair enough. And see you, Ali. Um, so the next part is about natural impact regularization. So like the hope is that the impact like factors like into these kind of like beautiful gears that we are seeing here in this drawing, where you can like point to them and like move the gears around, and that will be kind of like the impact. Um, and there are reasons to hope that we may in fact get this, because if you use like a general search algorithm or generalized planning where you recursively use the same planner for subproblems, then you really prefer that the subproblems are self-contained, are beautifully factored, don't have any large side effects, because if you are like if the subproblem solutions just have large side effects, they will mess up other parts of the search. So you would really prefer that to be simple. You really want bounded plans and bounded subplans. They are a lot easier to work with. Unfortunately, that doesn't guarantee safety, because you may have what Carl calls recursive compatibility. And that is something like if you are building a power plant, then you want to say something like, yeah, everything should be entirely paved over. And even if all the subplans require this, that's not a problem, because like even though it's a global effect that everything needs to be paved over, then all the subparts are compatible with that. So um, and unfortunately, the instrumental convergent side effects fall into this category. Like, for instance, every part of the plant kind of hinges on the AI being alive, and every part of it, like if the AI can like make itself smarter or something like that, then that will be something that even that all these sub elements will prefer. Finally, we get to the area of pivotal acts, the concept that we are right now on. If we are on a trajectory heading towards an existential catastrophe, can we do some kind of act that changes our trajectory towards existential safety? Well, if we there's this concept of the alignment tax, that doing things safely may be more costly. Um, there's a to do here about Stephen Burns' comments that I'd really like to see. But the obvious expectation is that if we don't do bounded optimization but do unbounded optimization, we are going to earn more money, right? That seems like the obvious expectation. It would be more effective to like not restrict the AI and just give it what we want. But there are reasons to hope for a negative alignment text, and in fact, a very strongly negative alignment text. So, in fact, doing things safely will be much cheaper. And the first is that if we do bounded optimization, we will have much greater predictability, and that is really nice, because like predictability is like a really important factor. And I agree. And unfortunately, I think what people will just do in practice, like we're not just competing against like things that are not doing things on a whitelist, but things that are input optimized, things that optimize for our approval. And so they may in fact be less predictable, but in the way they build fusion power plants, the unbounded maximizers, but they will be more likely to do something that we approve of. And I think that's why companies are going to prefer that. The feedback loop on effects is much richer than a simple reward, and that's of course true. But like the simple reward is also not how people would go about this. Like the doing reinforcement learning on, like you get reward for as much power you generate and use that to build a fusion power plant. That's not how people would actually go about doing this kind of thing. People already have like much better ways to do reinforcement learning than this extremely like just a simple reward. It's more interpretable, meaning that capability researchers will be able to improve on it, and that's in fact a really nice thing. If we can, uh, like, obviously, more interpretable is good if there is like a literal bug in the language model. Like you've coded something wrong, and then it says like if you say something like there's a Magikarp, and then the Magikarp token points to something wrong in the world model. In this kind of case, the fact that it's interpretable is a really nice thing. But if we want to really improve on it, then we need to like find new ways to think, and somewhat like because we can look into the world model, we can say, this world model would actually be better if the concepts were spatially organized in some different way, and improve on it in that way. And that seems like a much taller order. Eliezer Yudkowsky has a bet whether we will learn something which would have been um, unfamiliar to like cognitive science and AI back in 2006. Will we be able to like learn anything? Which needs to like this is like 20 years after. So is it more or less than 20 years behind? And Metaculus says like maybe on this prediction. So it's possible that we will learn something that like just a tiny bit, but going from that point to actually being able to improve is a really tall order. And in reality, that's not going to happen. In reality, what's going to happen is that OpenAI will not directly tinker with this matrix. They will just add more compute and build an even larger model, and that's going to like be really hard to be competitive with. So the overall,
Right.
uh,
Um, so so um, so I mean, OpenAI are they are sort of like experimenting with different architectures, right? Like, they sort of do, for instance, scaling laws and various different things, right? And in order to do these experiments well, they sort of need to know how well is this going, right? Like how well, and part of my point is sort of like, oh, if the world model is more interpretable, and if the entire system is more interpretable, then they will more easily be able to do all these experiments because they have much richer data. If you read Jonathan Wentz, then he has like a post called "You are not measuring what you think you are measuring," where he sort of goes into, if you want to have a good experiment, you have to measure a lot of things, and again, that's easier if you have a more interpretable model.
and I think you're right, and I think definitely that interoperability is going to help. But also, I feel right now, to a large extent, these models that OpenAI are using are like my intuition is that they are really poorly optimized and full of bugs to some extent. Meaning that the interoperability part that they are using is mostly like to try to like uh, this Gemini model is right now having some severe issues, and I think interoperability towards that is really valuable and something that they're absolutely doing. But I think like the next step, trying to like design the world model to try to make it more human understandable, seems like a much more difficult task. I agree. If they could do it, they would do it, and it would be valuable. But also that they are very far away from like rearranging the giant inscrutable matrix in a way that maps more cleanly uh, to human concepts. is my intuition. Like I literally don't know what's going on inside OpenAI. So this is kind of like my guess. That,
So I mean, I'm just less concerned about language models, right? So you know, okay, yeah.
and fair enough, right? Moves into the final strategic landscape where Carl is expressing substantial optimism about this paradigm. I think, like in a strategic sense, like obviously people should talk up their own proposals, but I think also like this is just too much, right? We're not really close to a solution, and in particular paradigms that are untested, that haven't actually been implemented, are, in my expectation, not that valuable. That you need to actually be able to present some real results before people take you seriously. Another thing that makes me think that my strategic view of the world is different from Carl's is that he feels that we may see people that just YOLOing, just try to, you only live once, so they will just try to build something that probably will kill us all, um, and buy Juliet. And I don't really know who would do that. I think people in AI safety almost certainly are not in this position, like Eliezer Yudkowsky. And
Isn't that sort of the position of OpenAI?
uh, I think OpenAI, yeah, that's an interesting question. Like, is OpenAI, is this something that will convince OpenAI to not um, uh, to stop their capability work, that it would be possible to build bounded agents? It's interesting. I did not, in fact, think about that angle. Um, would it um, that the problem is actually solvable? Hmm. That is actually a really good point. I'd like to just wrap this up, and then I'll get to that because I think that is a an interesting point. So my overall strategic outlook is that large language models are winning now, really, really big time. Like there is an enormous inertia behind them, and the trajectory is really, really, like changing that is very, very hard, and next to impossible. And my thought is that if we want to make any progress with work in this direction, then we what we really want to do is to somehow exploit the fact that they already have substantial, have good world models, and try to like do something bounded with them rather than trying to come up with something from scratch. So the overall outlook is that these three things, that it's more predictable, that it's better for capability, and I already forgot this last one. Sorry. That it's that we have a better feedback loop. Um, all these three things seems to be sufficient to make up for the alignment text because there is going to be a substantial amount of extra work. But we may, in fact, get enough capability from this that this will be the way people would do it from before. And Carl expresses some optimism about that, and I'm thinking like, yeah, if I thought this um, this made up for the alignment text to the extent that it could overcome the inertia, so people would start doing this instead of doing what they are like speedrunning Doom as they are right now, then that would increase my probability of Doom. But I unfortunately think that the alignment tax by this proposal is very, very large, and the inertia is also very, very large. Um, and Carl says that if it is true that it makes up for the alignment tax, then we don't actually have to do anything, right? Because if building safe AI is just the best way to do it, then like what's the big deal? And I think the big deal is that we have our work cut out for us. Because if it is in fact true, then we need to make a new S curve. Like right now, large language models are possibly on this S curve, and they will eventually be overtaken by something. And we hope it's something like this bounded optimization. But in order to get an S curve started, you need a lot of work. And like, if OpenAI is going to get 7 trillion, then we're going to need a two-digit amount of trillions. And if we don't have that, then we need to just work harder and smarter, I guess. So that concludes my presentation, and I wrote here that the discussion is not recorded because I wasn't sure we would record it, but we are in fact going to record it. So, Carl, thank you for your comments so far. And how do you feel? Should we start from the beginning, or also
Yeah,
how?
let's go to the beginning and then just take it sort of one at a time.
We will take it one at a time.
Um,
So this is my
let's
overall
see.
view on this. And is there anything here you want to complicate? Yeah, governance will need
Um,
to improve. Why do you feel governance will need to improve?
yeah.
Is there?
So I guess sort of the governance issue that I am most concerned about for this proposal is privacy laws, right? Because if AI companies are told you can't measure anything, right, then um, then they will have to use purely internal metrics, and then you have the whole unboundedness because it literally can't do anything bounded model based. It'll be like the worst case scenario, right? And of course, you could then say, oh, so we'll just explain to people that if we don't allow the AI to, do surveillance on them, then it'll destroy the world. That's not necessarily going to convince people. It's also possible that there are some compromises, right? Like, maybe we can measure things in general. But I guess there's the whole thing where maybe I possibly agree more with Elias Yudkowsky about the whole, politics doesn't really work and stuff, right? So, if we have any governance issue, right, at all, then, it's unclear that we can solve it. Like maybe we can log out, or, maybe this can be explained to people, maybe, but um, also because we're not just speaking governance in the context of AI. We're also speaking governance in the context of, what's going to happen to the rest of society, right? Like if OpenAI owns this AI, then who's gonna earn money from it? I guess OpenAI is openly in favor of windfall, so that helps, right? But what if we have like a competition between the US and China or Russia, right? If they have an arms race, then that can, lead to nuclear war, or whatever. Then that doesn't matter, right? Um, like just there's like an infinity of governance issues, and let's say we have 99% probability of logging out in each of them, right? And that's open 99 to the power of infinity equals 0. And 99%, that's optimistic, right? We need, like it's currently unclear, like governance might be getting worse and so on. So, it's not that I have a super specific one. If I had to pick a specific one, it would probably be the privacy one or like global security. But mostly it's just generic pessimism about politics.
Okay, fair enough. I think that sounds like a isolated demand for rigor in the sense that this will be a problem for most other proposals as well. Um,
No, it's not a problem for coherent extrapolated volition, right? Because it just takes over the world and then existing governance is irrelevant.
yeah, and also like
So
yeah,
and like all the traditional Mary research is in that category, right? So it's clearly a way that I'm going away from it, and it's not like I have an answer to Eliezer, right? Eliezer is going to say, well, governance is terrible, right? So we can't deal with the current governance. We have to take over the world, right? And I'm going to be like, I mean, you're not wrong, but I guess we should at least advertise that the traditional AI solution is to take over the world, and then
cool. Let's move to the second. Yeah, here's a question, like maybe an unfair question. Have you actually read the part of Plane Crash where they talk about corrigibility? Um,
Nope.
Fair enough. I can strongly recommend it. I think
Yeah.
it is in fact really good. And no, I should strongly not say it's really good. I will not say that it's really good. I think it's better than everything else, but it's not really good. That's what you
Yeah.
get. Yeah. Um, okay. So like taking orthogonal power-seeking action is utterly deranged. You use the word utterly deranged. Could you how would you like? I'm like taking orthogonal action right now, right?
Yes.
I'm not utterly.
So I mean, the um, the current society is sort of really weird, right? Because you can actually work in a job and then have excess money and then spend that money elsewhere. Whereas that's just historically literally not a stable pattern, right? Because you have the whole Malthusian thing where this means that there's support for additional population growth, so people go with it, right? But I mean, I agree that this is like not so deranged, or it's not deranged at all in the current situation, right? But I would actually rather like to zoom in on like earning to give and Marx Engels and so on. So Scott Alexander has an old post about how effective altruism should not be political, because he says he gives a lot of arguments, right? But sort of his final piece of straw is, you know, um, the person who's arguing that effective altruism should be political is saying, well, effective altruists are really smart and we're doing all these great things, and effective altruism has a great track record. So if we go and do some political stuff, then that's probably also going to go really well, and it's all going to be good, right? And then Scott Alexander says, if you think about it, what Engels did with Marx is basically the same as effective altruism. So it should be considered under the umbrella of effective altruism, right? But of course that led to communism and like huge numbers of deaths. So actually the track record for effective altruism is extremely negative. It's just completely terrible idea. And if we then look at it now, I think there's been some controversy about some effective altruist organization donating to OpenAI to get a seat or something. I don't know,
Yeah.
but like if you think that OpenAI is on its way to destroy the world, right? Then clearly we are contributing to destroying the world, and there's like a lot of things where just from the pure track record, it's not so clear. But I also think that it's directly related to the whole thing. Like, um, Marx Engels was not exactly bounded optimization, right? Like Engels funded Marx to come up with some idea, and he didn't necessarily tell Marx, oh, the results should cause this, right? And then Marx came up with some idea which was not very specific on the actual implementation or consequences, other than, oh, let's get rid of like the class and state and so on, right? So these are actually really great examples, like effective altruism and Marx Engels, of what not to do. um, if this whole proposal doesn't, like, if this whole alignment proposal doesn't get shut down but ends up looking good, right? Then I'm actually planning like a follow-up post that's titled something like, um, "Utilitarians are evil and must be suppressed." I mean, I've been a utilitarian for most of my life, right? But part of what convinced me of this post was sort of like understanding, like, what's wrong with utilitarianism, or like what's wrong with this unbounded optimization, right? um and actually, Scott Alexander and effective altruism also makes for more good examples. So part of what inspired me to it was, Scott Alexander was replying to someone who was going like, oh, effective altruists are secretly plotting to take over the world because they're utilitarians, right? And then Scott Alexander was basically, oh, but think about all the good things that effective altruists are doing. Why aren't you talking about those good things instead of talking about our secret plots to take over the world, right? And like that's sort of like the thing I'm saying people should not be doing, right? Like people shouldn't be trying to take over the world in order to do good things. Um,
Okay. Yeah.
there was more I wanted to say, but I can't remember if it was here or later. I think it was later with. So yeah, let's continue.
Let's continue. Cool.
Yes.
So, do you agree that this, like the intuition of a, oh, maybe, I think there is, Axel has a question.
Only if this is the time for questions.
Sure.
I wasn't sure we'd moved
Sure.
in. So I was just wondering about, I read your text, and I just want to make sure that I understand it correctly, that the whole idea about whitelisting, I mean, instead of trying to come up with all kind of ideas of what would be bad and then trying to make sure that that doesn't happen, which uh, kind of relies on that we can think right now of all the possible ways that things could go bad. And instead we just try to say, okay, these are the exact outcomes that we want. You have this example of moving a pen from one place to another place on the table. And I'm just wondering, in terms of these world models that you talk about, I might have missed it or misunderstood, but do you have a specific way of representing those? Is this like belief states? Are they predicates about,
So
and
that's sort of the big open technical problem, right? It's I sort of gesture at some formalizations, right? But I'm not really satisfied with any of them. So they're more like a wish list or here's something vaguely related. So I mean, I would love to say I had the solution, but that's the hard part. And we will actually be getting into one of the hard parts, but also one of the things that makes me think it's not as hard as it looks right here with the problem with unbounded optimization that Søren has. So the thing is, one of the simplest cases to sort of specify boundary is if you have some region of space, right? To say, oh, we allow whatever's going on there, right? But the problem is that's not how most of the that's not how most of the world looks. You can't just say like if you want to medically treat some person, right? Then they have some disease, but it's very close to all the rest of their body, and you can't just say remove the disease because it's all mixed together, right? And the person will not necessarily be in a specific location and all of these problems, right? But the thing is, much of this seems like it's also going to be a problem for capabilities. Like if you try to model a person, but the person can move to another place, right? Then if your model doesn't handle that well, then it will like easily forget which person it was and what they were doing and like what the properties were. So there's a need for a lot of development to handle these cases where it's not just a simple grid, but there's all sorts of different relationships and nesting structures and changing boundaries and so on. And I think much of that is going to be handled by capabilities, just because that's something you're also going to think a lot about when you develop capabilities.
And when you say changing boundaries, are you talking about that you also allow the system to by itself figure out what it needs to pay attention to? I mean, I guess before we were talking about whitelisting, which I do think is a good idea, but maybe you're also in a way just pushing the problem a bit further down the line. You're saying, okay, we're going to choose the things that we want to happen, and everything else should then stay the same. But that kind of relies on that you are sensing everything else. I think you talk a little bit about that as well, that the model becomes like so complex that it it's not possible anymore. Did you have any solutions for that? Not that you have to have all the solutions.
So I mean, yeah, it's sort of like the question of like how do we dynamically discover the boundaries? Like, let's say you build a fusion power plant, right? But then you learn that there's, you know, a power plant enthusiast group next by, right, who are going to try to spy on your power plant, right? Then, you know, by default, what my proposal would say is, oh, the AI would try to hide itself, but that's not very helpful, right? Like that would be the simplest way to avoid influencing these people. But you know, that's not very efficient. It might be more efficient to just give them the like a description or a tour of the power plant so they don't break anything, but do it. But in order to do that, you sort of have to dynamically discover that this is sort of a cheap and very unique. Like it's going to be a very specialized effect that only makes sense in this context, right? So you have this.
Yeah, I have a question. How do you prevent the system from like negating positive side effects?
Yes, so that's also a really good question, and I mean the proposal as I've written in the current draft actually has a very simple solution to it, which is the whole counterfactual surgery. But I don't actually like that, so I don't want to keep that. Um, so the plan that I sort of have, what should we say, so far is that let's say you teach it to bake you a cake or whatever, right? So it has come up with a strategy for that. Then it learns that cakes make you fat, right? Um, it will still know the original strategy that could be used to bake you a cake, right? So it will it will be able to say, okay, we have this strategy, but we have the problem that we have discovered this new effect, right? What do you want to do with it, right? And then, you know, you could say, oh, well, I am underweight, you know, so I'm actually great. Give me more calories. I need to be fatter, right? But you could also say, no, wait, I'm overweight. Try to not make me fat, which I guess would mean try to find some calorie-free solution, right? Um, so basically, the idea is sort of if you already know what the intended positive side effects are, and you know you have a language for expressing that and so on, then you know you can just say, oh, please make these positive side effects. If it discovers them later, right, then you know it can ask the user what should we do about this side effect.
And is the plan to like somehow get this capability within a large language model, or to come up with an entirely different architecture that's like an
So
expert system, or
so I guess that sort of gets into my opinion about large language models, right? Because a lot of people think, you know, large language models are going to be the future and so on, and I don't really think that because um, the way I see it is maybe it makes the most context, in most sense in the context of like you know general singularity theory and so on, right? Like so prior to all the deep learning stuff, right? People expected some singularitarians expected researchers to sort of make AI that's you know more and more adaptable until it can build some wisdom about how the world works and how to interact with the world, that like until it becomes better than humans at building wisdom, right? And then you know it's way more wisdom than people, and then you know it takes over, right? But what actually happened was that people made a very simple adaptability, right? Like we have a transformer which you can tell, oh, predict this text, right? And then you know we took all human wisdom and told the AI, hey, predict this human wisdom, and then you know it learned a lot about a lot of things that humans are able to do. But that doesn't mean it can generate new capabilities that don't already exist, a large language model, that is. So mostly I expect that large language models will be replaced with some new paradigm anytime soon. And like there are already lots of architectures that have been used traditionally, like AlphaGo is not, or I think AlphaGo started with it and then did self-play. AlphaZero, right? Like the state of the art in Go playing and so on are not using the large language model paradigm, and they're not going to ever, I think.
Actually,
Um,
you have a question?
Just have one last quick question. So as I understand it, this whole framework kind of relies on that we have to be able to predict the possible like effects. And I can see how it might be possible for us to get closer to predicting the outcome. Like you were referring to code examples. So you're referring to like you have the source code and then you have the actually executing the code. And executing the code could kind of, as far as I interpret it, be seen as the effect of that source code, right? Is that understood correctly?
I mean, if you execute the code, right, then you have a running computer program, right?
Exactly.
And if it's a user interface, right, then it has some inputs and outputs and so on, right? And this running computer program is the effect, right?
Right. So I see us possibly getting to a point where we can predict the program even before we run the code. I'm wondering about whether you're also assuming that we'll be able to predict just any like unforeseen outcome of or unforeseen effect of any action that the system takes, and whether this all kind of relies on that assumption.
So I mean, it's not just a question of like being able to like predict the entire effect, right? Because realistically, if you're going to do programming, then you're probably going to make bugs. There's no clear theory for why the AI wouldn't also make bugs, right? Sometimes you just predict wrong. So to me, what's important is like the whole question of the feedback loop, right? We wanted to be able to model the effects separately from the program itself, right? Like you have some intended program you want to make, then you make some code that you think will have this effect, right? Then you try the program out, and then you find a bug. So you learn, oh, the effect of this program wasn't what I actually thought, right? And then you can sort of update with that and like go and have a feedback loop and improve your capabilities.
Okay. And speaking of these feedback loops, you also mentioned that that for bounded optimization, there isn't really like a good way of using the feedback loops. And I had a little bit of a hard time understanding why that is. Does that have something to do with that? Because you have, the way I see bounded is both this idea of not having only the things change that you've kind of whitelisted to change, but also you could see that as just deciding that X can only be a certain value, right? Or that your variables that can only change in a certain way. And is there something inherent in that prevents a good feedback loop? Or
I don't think I've said that it prevents a good feedback loop.
okay, sorry, maybe I don't want to misquote you. Maybe just that there wasn't a good way yet to, but lacks theory for how to use a feedback loop to generate new capabilities. Maybe that's just the part I didn't understand.
Oh, yes. Wait. So can we find the slide in the shared screen? Because yes.
So we are going to, we're not here, right? It's not this, it is,
Yeah.
let's see. I think this is slide we're talking about.
Yeah. So I'm not sure
Hold
this
on,
is the
actually,
slide.
we're passing 2 hour mark, so Carl, at some point, if you want to tap out, then you are of course free to do that.
I mean, I can continue. Okay. I don't think this is a slide because it doesn't say. But so the problem isn't that I think it's impossible with getting a feedback loop for bounded optimization. I actually suspect it will be much easier than for unbounded optimization because you avoid a lot of problems. The problem is we don't have a formal theory for it. And I think the reason we don't have a formal theory for it is sort of the formal theory for unbounded optimization cheats in a sense, because usually you say, oh, we argmax over the expected utility or something like that, right? And that's fine as mathematics, but then you're saying, oh, we know the utility function, we know how to compute the expectation, and we know how to do the argmax, right? Like, it implicitly assumes that you have all these tough engineering challenges solved, right?
Mm.
But once you actually need to, for instance, I mean, this first example was, okay, the utility function, right? But, the entire alignment problem is we don't know the utility function. So imagine you're not allowed to write you have to actually write a function that does what you want, right? Then suddenly we don't have a theory for unbounded optimization. And imagine you're not allowed to use an expectation operator, right? You have to actually, write the world model or like the computer program that, what models the world in some way, right? Like, again, that's not really that's suddenly much harder, right? Or you're not allowed to use argmax, right? You have to actually specify the search procedure, which goes through and solves all the constraints, right? And then my claim, like one of my follow-up claims, is that once we have a computational intractable solution to these, then that's probably gonna make bounded optimization much easier to describe. Because, for instance, the whole natural impact regularization point I made, right, is that it's very hard to actually do argmax with unbounded plans, right? Because they have all these side effects that destroy all the things, right? So if you want to actually implement argmax, then it's much easier if you have if you have like some language that can talk about these bounded things.
Okay.
So but the trouble is also, if we want to try to formalize the bounded optimization, right? Then many of the things that we want to talk about, like these world models that have a nice structure of like being factored spatially and so on, right? They will be they will not tend to be favored if you don't have these computational limitations, right? Because you can just like if you are allowed to use argmax with no computational limitations, then you can just model the butterflies wing flaps, right? And
Mm-hmm.
nothing goes wrong with that, right? So once you start incorporating some of these, then you start incorporating all of these simplifications that are needed to make things computationally tractable, and those are the ones that we're also going to rely on to make it bounded.
Okay, that makes a lot of sense. Great.
Question two.
Thanks a lot.
Yeah.
I'm gonna go for tonight. I gotta get some sleep, but thank you really much, Kyle. It was really, I might send you some questions as well, if I may, because it's very interesting.
And maybe you can join us on Saturday here.
Yeah,
in Midfield.
that would be great. I'd really like that.
Okay.
Cool. See you then.
See you.
Bye.
Wait, what's happening on Saturday?
I'm hosting the Astral Codex 10 Less Wrong Express meetup here, physically. So if you come to Denmark, you are very welcome. Yeah, yeah. So we are hopefully yeah. I had another question for Carl, and I think unfortunately I forgot. Yeah, how do you think this is going to scale? Like, so a lot of the issues you are pointing out with like, if you don't have the utility function, but you actually have to specify, and you have to specify a search procedure, and you have to do all these things. It seems like the kind of thing that as we scale and as we move into the future, that's going to be less and less of a concern, right?
So I mean, if we scale the computational inputs, like
We scale everything up. We scale the amount of compute that we
I,
do.
I think you actually have like a slide about how compute and so on is instrumentally converging, and like that these are that we have like different examples of what we
I think this.
mean by. I think it was a different one.
Okay. So.
Like
Mm,
like where I think where you said, you know, that this isn't what you would think of as instrumental conversion. The things like I think it was with the bottlenecks.
yeah, let's find the bottlenecks. It was I think here. This is the bottlenecks. This is the
Yes.
bottleneck size.
Yeah.
So, like my thought is that right now, bounded optimization could, in theory, have some advantages over unbounded because when you actually try to implement unbounded, then that is kind of hard. Um,
Mm.
and I would expect that that may be the case right now, but if we look at the trends, then in the future probably we're gonna have way more compute and we're gonna have way better algorithms. And so the problems that we have right now is where we need to like actually specify these things are going to become smaller and smaller. And so the
Mm.
advantage that unbounded optimization will have will increase compared to bounded
Yeah.
optimization.
So I think, you know, this gets into approximately everything of like central importance, because um, first of all, there's a simple answer, right, which is asymptotics, right? You know, if bounded optimization is asymptotically more efficient, then, you know, you might not do it, right? And there's the other simple answer, which is, you know, you're right, right? If you throw more resources at things, then stuff gets easier, right? Those are the simple answers, right? Um, but I think like the deeper answer is that much of what we want from intelligence is like easier and better ways of doing things, right? Like we could take resources that we allocate to one thing and then allocate them to AI, and then we can more easily make an AI that destroys the world. That's true. Um, um, but we would of course love, I mean, if you look at, you know, what are people currently doing with AI, right? They're doing all sorts of crazy quantization, and like actually training the AI starts being like a major logistics problem because they have to optimize, like I think that, you know, you hear in the news they're optimizing the connections between servers and all sorts of crazy things like that, right? um, you know, the resources are bottlenecks, right? But they're also bottlenecks in the sense that if you can find something that uses less resources, then that's also great. There's also the fact that currently we sort of have the assumption that GDP per capita will be growing, right? Like the point of the world is to consume as many resources as possible per person. Um, but um, so I think that that sort of connects to the philosophical issues, like um, maybe the reason that the whole theory of unbounded optimization has become so popular is that, you know, in a world where we have increasing access to resources and so on, you can sort of grow exponentially with these resources, and then, you know, basically the winners of society are the ones that have this unbounded optimization, right? So I think, you know, there's the whole practical and, you know, philosophical and so on, right? Um, but yeah, I mean, in terms of AI, right? Anyone could invent, oh, I need more funds and so on, right? Like anyone could throw that on it as a solution. So the thing we want from AI isn't really a machine that says, give me more funds, right? Like you could write a simple one-liner in Python, print, give me more funds. That's your AGI, right? So what we are interested in is, you know, finding the bottlenecks that help us without funds. Yeah, I mean, I'm sort of getting it's saying a lot of different things, so it can take a bit to process.
Fair enough. So the and I think like I'm trying to come up with some good examples of problems that we don't solve in this particular way. Like for instance, like um, if you are trying to find the love of your life, then the thing you're probably not going to do is like take a very gradual approach and then like every year find a 10% better girlfriend, or let's say upgrade your wife like continuously. It's probably going to be a very different process that you use to figure out like a lot of introspection to figure out who do you want, and then at some point you like the it is not a like many things, like also like I don't know, deciding to declare war on Ukraine or something like that is also some extremely discontinuous things.
Yeah.
And there are a lot of really discontinuous things and things that have like very dramatic effects. Like if you have a self-driving car, and then like whether you decide to turn left or right, or if you decide that this is something or the other, that's something where you are strongly you need to get it right, and like the world is not discrete in some sense. Does that make sense?
Yeah. I mean, it makes sense. So, I don't necessarily mean that people should always solve things gradually, right? The bottleneck is more a question of, um, let's say you have something that you predict should work, right? Like you predict here is a plan for a nuclear power plant that should work. Now I try to build it, right? Let's say it doesn't work, right? Then then that must mean your predictions were wrong somewhere, right? Um, so you go as I say, like measure all the things, right? Like that's one of the big parts of the post, right? So you go measure all the things and figure out where was your prediction wrong, right? And then you found some place where you expected that the nuclear power plant worked one way, but then it worked another way, right? Then the simple attempt would be, okay, let's just fix that, right? Like let's try to make it work, right? And but if it turns out that after updating and realizing this didn't work, maybe you learn, okay, I don't actually know how to do this, right? Then once you learn how to solve this sub problem, right? Then you would expect the rest of your original plan to work, right? So in that case, if you build a solution to this relaxed problem where you just, I don't know, have a plasma of too low, right? Then you expect that you can just like get it all running, right? And of course, that expectation may be wrong, right? But then you have another prediction error that you can go in and debug. And of course, this is like a very different type of problem than finding the love of your wife, or like turning with the signal and so on. So I don't necessarily like think that the solution mechanism would end up looking exactly the same for those other problems. If you want to pick one of the other problems, then we can try to think about what that would look like. But of course, part of the problem is still we don't necessarily have the algorithms yet, right? Like that's the big.
Sure. So this, I also don't like feel this is not a very central application to. This feels like something that is like a
Oh,
suggestion.
I would also say, so given these clarifications that I just made, I think this is quite similar to how humans solve problems.
Interesting.
Like
Yeah.
if you're making a computer program, right, and you write some code, you think it works, then it doesn't work. Okay, then you'll try to figure out what went wrong, and once you've found out what went wrong, you'll try to like fix that one thing, and check, does this one thing work? Like maybe you write a unit test or something, and then you go on.
Yeah. Sure. Um, I also feel this is not like a load-bearing part of your proposal. In
Yeah.
that if this is changed, but the rest of the feedback loop and the plan effect mapping basically stays the same, then precisely how these kind of problems are solved is like you could imagine doing it in other ways. You could so um, I want to talk about something else. Let's see what I want to talk about. I'll just go back and see if there's anything here I want to talk about. Oh, what is not an effect? Um,
Um, I mean, I guess it's difficult, right? Because effect is more like an ontological term, right? Like, what is not a wave, right? That's um, um, because like um, often when you talk about, you know, something that's in a category versus not in a category, it's because the category is sort of like propositional, right? Um, whereas I guess part of my idea is that we would have something that learns to represent the entire world in terms of effects, maybe. I mean, and, it's still kind of up in the air. Um, um, but I guess if you have a utility function, right? A utility function does not specify an effect, right? Because it takes the entire world state, which might be the sum of many effects, or however we choose to represent it, right? Like, and then it spits out a real number, right? So it has like exponentially more data than, well, way more than exponentially, right? Because if you take a sum of many effects and then yeah,
sure.
yeah.
Okay, let me give a suggestion for like a really bad suggestion for a definition of an effect, like something
Mm.
that can be expressed with a simple English sentence. Simple being such that like there's a single subject, a single object, single verb, something like that. That would be an example of a the set of all things that can be described in this kind of way could be the set of effects. Like this would be a
I don't think that's entirely off track, right? If we imagine that humans are doing some sort of like bounded optimization thing, right? Then, a lot of language is gonna be optimized for that, right? Like, okay, let's say you use an AI to make a cup of tea, right? But it's an unbounded optimizer, right? So it destroys the entire world and tiles it with cups of tea, right? Um, Now, you wouldn't describe that as the AI made me a cup of tea, right? You would describe that as the AI takes over the world and destroys everything, or something like that, right? So the way people use language, I think, already aligns a lot with sort of my proposal, right? Like people try to sort of describe the total effect of what they're doing in some sense, right? Of course, it's easy to say that, right? But then the question is, can this be formalized well enough to work in AI, right? Like, but I think it's not unreasonable to think of an effect as just something that's describable with a piece of language.
yeah, like you.
Um,
I think
yeah, can I ask a question?
sure.
Hmm?
Yeah, so it's like, I don't know, it's like, it feels like, to me, an analogous situation might be if you were in 1860 and trying to describe how to land men on the moon, and you're talking about like the spacesuits and what the rocket or I guess bullet, given the thinking of the day, would look like, instead of like actually explaining the process by which we get to the moon. Like, because the figuring out how aerodynamics and like the theory of how to get an object to the moon and land it safely is like the hard part, and the easy part is designing, vacuum-proof suits and how and like what the exteriors of an aerodynamic object would look like. What's your plan on tackling the hard part?
So I mean, I think I emphasize many times in the blog post that I don't have a solution to the hard part, right? And sort of what I currently do, right, when I try to come up with a solution to the hard part is that, for instance, I think of, oh, what is like a self-supervised learning algorithm we could use, right? And what sorts of models would that then likely generate? and how can we like would those models then expose like a type signature, like an interface that works for this proposal, right? Because the thing is, the notion of effect is not really something that we get to choose what means, right? That's going to be an artifact of the world model, right? The world model learns some structure, right? We probably have some loss function or something, and then we get a bunch of training data from somewhere, and then we stuff that into the neural network, and then the notion of effect is, whatever IO structure this neural network learns, right? Like, and we don't yet know what that structure will be because we don't have a sort of solution to the capabilities issue. But basically, when I sort of think about how do I solve this problem, right? I think about, what would possible architectures or loss functions or whatever, and that's not the only angle I take, right? I take various different angles, but like this sort of gets at the more direct one, right?
So this is maybe a stupid question, and this may be because I'm tired, but I do remember that there was some way, if you have a specific neural network that has this kind of superposition where some concepts are like a single neuron, um, uh, what's it called? Um, a single neuron represents many concepts at the same time,
Superposition.
and there was a way, I believe, to from a small network with superposition make a dramatically larger neural network that didn't have this superposition.
Sparse autoencoders. So
Yeah. So
yeah,
thought is like, imagine that you say, okay, effects will be simple English sentences, and then you
yeah.
take the GPT-4 neural network and just make it one enormous then you could like literally factor it out into sub elements that can contain basically that each of them
Yeah.
map cleanly to an English sentence.
Yeah. So this gets at some things, right? There's a lot of things overlapping here. So the problem with sparse autoencoders is that they basically don't work at the advertised thing, right? Because um, they capture the like if you have multiple features that are in some sense logically independent, like they describe different concepts in some relevant way, right? Then a sparse autoencoder might still decide, hey, I'm gonna use one dimension for describing these two things if I if these logically independent features are correlated. Because basically that's what the loss function favors. This might not actually be a problem for my proposal because it might still be um, sort of things that are sort of intuitively related, like different features of a power plant are all going to be correlated, and that's very useful if you actually want to create a power plant, right? Then it's actually nice that you just have a single dimension to represent that. But the problem is that this means it will not be able to represent sort of new combinations of things, right? You won't be able to say, okay, we have this power plant, right? But like take out the coal part and put in the fusion part, right? So it's, you know, um, I mean, one could say that the sparse autoencoders are sort of related, but I'm not optimistic about them mainly because they're sort of too. Well, there are many reasons I'm not optimistic about them. One of them is that it's what I just said, and another one is that um, it's it's sort of trying to solve the hardest version of the problem, right? Because you have a model that was just trained in whatever way that was not at all optimized for our whole world modeling thing, right? It was just, oh, we have a lot of internet data, let's try to predict that, right? Um, it's the worst case scenario for doing anything. Then finally, um, The sparse autoencoder is primarily trying to do mechanistic interpretability, right? Where it understands, what's going on inside the neural network, right? But I don't actually think my proposal needs that, because what you sort of need is the ability to act on like the boundaries. Like right now, if you take an image model, I guess not right now because we started using diffusion models, but it used to be that if you took like an image model, right, a generative adversarial network, right, and then you have some pictures of people who are smiling and people who are not smiling, and then you can find like a difference vector or something like that, right, where you don't necessarily know what's going on the inside, but you can still find features that are meaningful and useful and do transformations that are useful. And that is mainly using sort of the I/O interface of the model. And I think Alex Turner is working on the whole shard theory, right? Where they've discovered that they can control a mouse in a labyrinth or something like that, right? And I think as you start getting deeper and deeper into the network, it's questionable whether they're gonna succeed, right? But clearly, the track record shows that as long as you're staying very superficial in the networks, then you can just find some nice features and do something with them.
So, like, I may have to tap out of this discussion, unfortunately, soon. So, unfortunately, I have to get up early tomorrow. My wife is currently on a business travel, so I have to look after the children. So, I'm wondering, Carl, do you have any thoughts where you think this would be really nice to talk about at the end, or perhaps we could talk about this later, or talk about this Saturday, or
Let's see. So I think the key question is like, which would we want to talk about if there's like a last thing to talk about?
otherwise we can just say we'll talk about this on Saturday, and I'll just say thank
Yep.
you for joining us. I'm really
Yep.
happy, and I hope we'll be able to continue the discussion. And good luck with like finishing the draft.
Yeah. So I guess there were some of the later ones where I was also not in like full agreement, but I guess that will be discussed later or like be addressed in the text or something. I guess we'll figure that out.
Yeah. So thank you, and also to the few who are still left, Tim and Laming. I hope to see you again in 2 weeks. And yeah, thank you for your patience. If you want, you can stay and discuss without me, without the recording. But I will probably be. I need to get some sleep, unfortunately. So I will stop the recording here. Thank you again, Carl. It's been a pleasure.
See you.